Okay, so we are going to do one more example of the problem-solving process with Newton's second law, and this time we're going to look at a non-equilibrium system using Newton's second law to help solve for motion. So the question is, it's going to be example 6.3, again, to kind of give you that frame of reference of how I do things a little bit differently than the book, and a process that works really well. So a 1,500 kilogram car is pulled by a tow truck. The tension in the tow rope is 2,500 newtons, and a 200 newton frictional force opposes the motion. If the car starts from rest, what is its speed after 5 seconds? Now I'm going to run you through the entire process, and that means getting some information maybe that we don't need to solve the problem, but to really flesh out the whole process, which will serve you very, very well, and will help identify what you do need when it becomes a little bit trickier. So, first step, identify that object. And in this case, it's the truck, car, I forgot already, it's car. Okay, so we've identified the object, and now we're going to draw a picture. We're going to draw a picture of the car that we care about. It is being moved along, it's being pulled by a tow rope, we know friction is involved, and it's moving in the rightward direction. It's accelerating, and it's accelerating to the right according to the problem. It is starting from rest, and we want to see what the speed is after 5 seconds, so it's getting faster. Now this is going to have some kinematics flair to it, so in this case we might want to consider putting on an origin. Now we're actually interested in what is its speed, and what I would encourage you to do is say, all right, well that's a kinematics process, so let's start with the kinematics process. See where it leads us, and then see how forces might come into play. So in the kinematics process, after we've sort of identified things, and before we've even drawn a picture, we have identified what begins and ends the motion. So it begins when the car is at rest, and the ends after 5 seconds, 5.0 seconds. We've identified our origin, and we've identified the direction of the motion. Acceleration is to the right. So now we make our list of notes. X initial, final, V initial, V final, acceleration, and time. This is in the horizontal direction. Now we typically haven't identified that in kinematics unless we were dealing with two-dimensional motion. But the reason I want you to start thinking about that, what is the direction of this motion, is because if we need to use forces, I need to identify a coordinate system. And so the motion is in, the acceleration will be in the horizontal dimension, and that'll guide us when we get to analyzing Newton's second law. All right, so initial position when the car is at rest. We've identified that as x equal to 0. Final position, we don't know. Initial velocity, it's when it's at rest, that's 0 meters per second. Final velocity, we don't know. It says acceleration, oh, it's not given, so we don't know that. But we do know that the time is 5 seconds. Now, the problem asks us to solve for the final velocity. That is our variable of interest. We know that V final is equal to V initial plus acceleration times time. Well, V final is what we want to know. V final, and this happens to be in the horizontal direction, equals V initial, well that's 0, plus my acceleration, and again horizontal, times 5. So V final, what I want to know, is equal to the acceleration horizontally times 5. Well, that acceleration isn't given, but we know that forces cause accelerations. So if I don't know acceleration through kinematics, I can do a force analysis to get that acceleration because it's the forces that are causing it. So we shift to a force analysis. The physics tells us, the process tells us what we need to do. It's great. You don't even have to worry about thinking of it in advance. It guides you there. If I need acceleration and I can't get it from kinematics, I go to forces. Okay, well I have my object and I have my picture. I'm going to be explicit about defining a coordinate system. I'm going to align it in the direction of the acceleration, and then that's going to make life really easy when I solve for horizontal acceleration. All right, so what are my interactions? Well, one thing that's interacting with the car is the force of gravity. That's between the car and the earth. It points down. Another thing that interacts with the car is the tension. That's between the car and the rope. It's pointing to the right. And of course, I also have the normal force. That's between the car and the earth. And it's pointing up. And last but not least, I'm told there's a frictional force. And that's between the car and the earth, the ground, and it's opposing the motion. The car is moving, so it's kinetic friction. So there's all the information, all the interactions. Let's put them together in a free body diagram. So here's my car. I have the force of gravity. Equals mass times gravity. I have the normal force, it's acting up. The rope is causing a force to the right, and friction is causing a force to the left. All right, so my four forces are identified on a free body diagram. I now separate those forces into their horizontal and vertical components. So I have horizontal and vertical components. I have four forces, 1, 2, 3, and force number 4. All right, so force number 1. Force number 1 is not acting horizontally. It's only acting vertically. It is in the negative direction. And it's actually given to us. It tells us that I have a 1,500 kilogram truck. Well, we know it's minus mg, and 1,500 times 9.8, that gives us minus 14,700. All right, force number 2. Well, that's only acting to the right. It's a positive value. So positive tension. It tells me that the tension in the rope is equal to a positive 2,500 newtons. Nothing in the vertical direction. Force number 3, well, that's our normal force. In this example, there's nothing in the horizontal direction. And I have a positive upward force in the vertical direction. That value is not given to me. And force number 4 is a frictional force. It's only in the horizontal direction and it's negative, moving to the left. And it is given as 200 newtons, so I want to make sure I keep that as my negative value. It does not have a component in the vertical direction. So I've identified, separated the forces into their horizontal and vertical components. And now I sum them and apply Newton's second law. So in the horizontal direction, the horizontal sum is going to equal the mass times the horizontal acceleration. I know there's a horizontal acceleration, so that's going to sum to ma. In the vertical direction, it's equal to mass times the the vertical acceleration. But the car's not changing its motion in the vertical direction. So these forces are going to sum to 0. So applying Newton's second law conceptually and then using that information mathematically. So the sum of the forces horizontal are equal to 2,500 minus 200. And that's equal to the mass times the horizontal acceleration. So I have 2,300 is equal to the mass, which is 1,500 times the horizontal acceleration. And the horizontal acceleration is equal to 1.533 meters per second squared. That's what I was going after, so I can stop here. I don't have to analyze the vertical direction. I can come back over to my kinematics, and my final velocity is 1.533 times 5, and I get 7.7 meters per second. So that is how I determine my kinematics when I'm stuck without an acceleration. I look to what causes that acceleration. It's forces. I attack with a force analysis problem. When I get what I need, in this case in the horizontal direction, because I've identified my coordinate system in a way that works for me and works for the problem and is smart. So we want to be always to be clever. And then I can solve for what the problem is interested in. All right, so remember that kinematics process. Apply the force process, put them together, and we can tackle pretty much any problem we got. Good job.